discuss because I'm specifically looking at modeling that methane release that we're discussing as a production of coal. And we're trying to predict what those concentration profiles may be downwind so that we can test the effectiveness of this system that Amber had previously described. So for our project, we set out to develop a methane detection system for longwall coal mining that can, one, stand alone to continuously monitor methane emissions and store and process that data to create some kind of feedback system with other processes in the mine. I'll explain a little more what these processes include in the next slide. But for this presentation, I'm just going to specifically discuss the CFD and modeling approaches that I've currently been working on to give us some sort of simulation that can generate these methane concentrations to assess the effectiveness of our system. This is just a small part of the whole project that we've been working on to date. So I'm really just trying to get some initial baseline results at this point to develop a future strategy. So here I've listed a few things that I want my model to incorporate. I want to really be able to kind of capture the flow as it enters and exits the mine. I'll discuss where these issues lie. These methane sources and their magnitude, so where they're coming from, where the significant sources are, and then coupling that methane release with the fresh ventilation air as it enters the longwall section to derive these expected concentrations downwind. So here on the left, we have a pretty good shot of what the typical working area of an underground longwall coal mine looks like. All the coal being cut here, you can see on the right, all this black stuff, here's the coal. And this is done so with the shear. Like I said, Amber has previously described some of this. That's this thing right here in the middle. And then all these yellow things are the shields here on the left. And we can see only about 10 of those here, but there would typically be about 200 to 220 of these shields along the entire longwall section. And I've included the dimensions of a typical longwall here, so you can see where that length could be 1,200 feet, 300 plus so meters. And then on the right here is the top view of the working section, and this depicts the ventilation plan. So this big blue arrow here, what we see here, this big blue arrow is really what you're seeing here in the left picture. The head gate is where the air enters, this tailgate is where it exits. And that picture I just showed in the previous slide was of a big ventilation fan. And that's what pulls the air in from above ground to supply this longwall. And that could go up to upwards of 3/4 to a mile all the way underground. So it's pulling in hundreds of thousands of CFM to meet this. And this air has to make a few splits. Like I said, I'm not going to get into the whole workings of a coal mine, but there's a lot of room for this air to kind of move around, and it has some obstacles it has to cross to really get to here to do what it's supposed to do. So the flow field is somewhat simple. Turbulence is present and can be greater in some locations as opposed to others. Some of the contributors include the shear, which is primarily the main obstruction, the tight checkpoints at the entrance and exit that I was talking about, and the shield components. So here we have a flow study that was previously conducted to assess the flow around the shear and how effective it is at reaching the face to ensure that the methane is diluted at the cutting head, since the shear is the primary source of ignition. So we can see here, this kind of looks similar to the top view of the ventilation plan from the previous picture. Air enters here on the right, and then it has to make this tight checkpoint here where it makes a 90-degree turn and comes along the face, and then exits. And zoomed in here is the shear. So we can see how this air cooperates around the shear, because its primary goal is to dilute the methane that's being released at that cutting face, since it's the main source of ignition. So turbulence can be both beneficial and dangerous in the working environment. The entire purpose of the fresh air is to mix and dilute the methane that is being released from cutting the coal in the working area. But with that being said, in the event that an ignition occurs, the turbulence may promote the combustion process, create more of a threatening explosion or runaway. We do want this mixing to occur though, so that the time scales are small and that the methane concentrations within that general area are more uniform. This allows us to more accurately detect the real concentrations by eliminating fluctuations. So here I've included some simple schematics of our system. And like I said, I think Amber explained this a little bit more. These are our nodes. Here's a side profile where we sample from the front and back. And this is, I think, the same picture of our Reedsville farm as we've implemented it here. So speaking of these timescales and the detectability of our system, here are some system limitations that are inherently present that we must deal with. The sensor's response time being the biggest one. You can see here the sensor requires at least 10 to 30 seconds. This is the rise time of this sensor that we've tested. Our system has two sensors, so this could change depending on what sensor we're talking about. But if the methane concentrations are constantly fluctuating, then the response will give false low readings. But this is also an entirely different discussion of the project. So I'm mainly just focusing on the CFD stuff here to generate these expected methane concentrations as a result of the ventilation rate and the methane released from producing the coal. So I use ANSYS Fluid as the solver for this work. On the left are the two transport equations that are used among the standard K epsilon turbulence model. And on the right are the equations being executed to model the chemistry interactions of the methane and air mixing to produce some resultant concentrations from the turbulence. So I have the species transfer model turned on. And it's only modeling the two species right now, methane and air. So here are a list of a few characteristics of the K epsilon model. The flow domain at full scale is rather large and can be computationally expensive for a 3D simulation. So its robustness and economy are good features since the mixing and flow itself is rather simple. There is no combustion and other particles being accounted for here yet. So by incorporating both the turbulence model with the species transport model, is a function of the statistical velocity gradients, then some first pass predictions may be able to be made to generate these methane profiles and can be used to assess the response and effectiveness of our system. So here I've included some of my results I have so far. So this is, I first did a 2D analysis. And this simple rectangle you see here is the top view of that long wall section to full scale. So this is about, I think, 1,200 feet, 300 meters or so. And the air is entering the left here, and everything exits out here. This top part of the domain here is a wall. And then I have the methane being released as a constant flux along this entire lower boundary. Now these flow rates are pretty small. We're talking about around 2 meters a second is what the ventilation velocity is. And that methane release is something that we've had to try to derive. And it's a very small number as a function of cutting the coal. But as you may expect, you get a pretty linear concentration profile as you proceed along this long wall face. With, like I said, the flux being along this entire boundary down here. So then I tried to more accurately represent the actual geometry with taking some of the complicated features out, such as the shields, because this is still for the full scale. So here's a general geometry that I created that tries to mimic this shield profile. Like I said, there's no shear and no shields, but this is essentially the effective flow area that I tried to capture here. And similarly, I have air coming in from the head gate, which would be along here, and everything would exit down here on the other side. I have this now, I have the only source of methane being released from the face. So we're saying here that we're assuming that methane is only a function of cutting coal at this point. Realistically, it's naturally being desorbed from the coal all around. So really there may be some type of methane flux everywhere. But we're saying that it's just a function of cutting the coal. So I have it defined as this face. You can see has it, these concentrations propagate here. And then here is a plane cut in half of the same section. So this is a transient model, but it's run to steady state. This was the maximum concentration that I was able to achieve, which seemed to take about 200 seconds. Because like I said, the flow were defined at 2 meters a second at the entrance of this thing. And the methane was something to the order of like to the -5. So yeah. And that's pretty much about it. Here are my references. Thank you, and I can take any questions now.
Okay, thank you, our speaker. Thank you. So please, questions from the audience first. Please. Okay, then let me ask something. So, okay, so basically, so this is ANSYS Fluent simulations. You use ANSYS, right?
Yes.
For the pictures. So is it parallel, or you do calculate on one processor, or it's two-dimensional analysis? So do you use one computer, or it's parallel computations?
Yeah, this is just on a single computer. And I don't have, like I said, this is kind of some first stuff that I've just been doing over the last several weeks, or we just turned our final report in, so I was trying to get some stuff kind of turned out to kind of make a future plan. So yeah, it's just on one computer. I haven't optimized anything with any of using multiple processors or anything. I've actually was able to run it off my laptop as well for the 2D stuff.
Yeah, because it's 2D. So could you please describe a little bit about your simulation? So what is resolution? What is grid size? What kind of model you use? Anything you remember?
Yeah, so I don't have it pulled up right now. The grid size, I did do a bit of a study. For this, I just simply used number of divisions. So I put like a face mesh over this, and then I ended up working down the divisions until my results came out very similar. I don't exactly remember the element size or the number, the count. I want to say it was several hundred divisions along the, or 1,000 divisions, maybe even along this length. Maybe I divided it by 25 so that each block was maybe a meter by a meter. Like I said, I have the energy equation turned on. I have it's a transient model, and I like I said, implemented the K epsilon model as the turbulence model, and then I have a species transport running with only the methane and air being defined as the two species interacting. And there's no ignition. Like I said, it's not an ignition. It's just a mixing thing. So I don't have any source of ignition or anything like that.
But but if you say transient, so is it like direct numerical simulation, or it still runs? So do you resolve time in full?
What was that?
So is it direct numerical simulation, in fact?
Yeah, I believe so. I don't have set any of the criteria for once it's reached what are they called? For it to end the model, or once everything's converged. I don't know if I've reached those or not. Like I did have some issues at first, because this is really my first kind of full attempt at doing CFD stuff like this. So I had some issues with things converging and then kind of solutions running away with the grid or the meshing. So once I seemed to fix those issues, I refined the mesh a little bit. Then I finally started to get these what appear to be a little more accurate profiles. And I still kind of had some issues with the 3D stuff. Like I said, one of which is just a timing issue. I didn't have much time to work on this yet from the stuff that I'm presenting here.
So what you present in these plots? What is color? What color mean here? It's verticality or velocity? What?
No, so this right here, I haven't included a velocity profile. This is the mass fraction of CH4. So the upper end of the scale here is 3 to the minus 2. And like I said, the color contour here is the mass fraction of CH4, methane.
Methane. Okay, yeah, okay. And so in Reynolds number, in your case, it's quite small, I believe, right?
It should be, I'd imagine it's quite small. Like I said, everything is incompressible low. It's 2 meters a second.
Okay, so this is incompressible flow, no combustion, definitely. So then, so in terms of fluid mechanics, so how you distinguish methane and air in that case? Because like, yeah, chemistry is different, I know.
Yeah.
But if you consider like from fluid mechanical point of view, so what is air? It's oxygen and nitrogen, correct?
Right.
So oxygen, it's like O2 and N2. And here you have CH4, and remember that one molecule of methane is actually nothing but like one atom of oxygen. So
Yep.
how, so from your numerical point of view, like you say, this is methane concentration. So how you distinguish methane from air?
So
Methane and air, right? You have two mixtures.
yeah. So one thing.
Yep, please go ahead.
So one of the things I went back in to look into as far as the modeling stuff go and how I define these parameters with that species transport. Like I said, I wasn't entirely sure at first, since it's specifically there to kind of mainly model the combustion and contains all these species. I had to make sure, I went back and had to make sure that the air was actually O2 and N2, because I wasn't exactly sure what concentrations or percentages, if it was 70 and 30 or 60-40, whatever, of O2, N2. At the time, I turned off all other species and I just defined at these boundaries here along the face, I set it to be 1, which would just be full, just a CH4. And that's when I kind of realized, oh, I better go back and check to make sure that these, like we said, these chemical interactions or concentrations are actually correct. And it appears that I had things set correctly. But it is defined, like I said, as a velocity inlet, a flux of just pure methane coming in along this face, and then air. And then due to the turbulence would dilute that.
I see. Yeah, that's I see. And what about other difference? Yeah, so I see what you mean. So and this is mass fraction, right? Methane is a mass fraction.
Yeah.
So what you say, 70% it's in terms of mass, right?
Yeah.
Mm-hmm. Right. Okay. Okay. What about other differences between like methane and air? So do they have like different viscosity, different transport properties in your simulation?
Yeah, no. So like I said, I haven't gone in and self-defined anything other than simply turning on those species and defining exactly where they are, where they enter from. So like I said, the air is entering from here. I have this whole face right here defined as just an O2 or an air inlet. And then as it proceeds through, it's picking up the methane from the wall here. I haven't gone in and changed anything really specifically. I did mess around with, like I changed, because we're assuming that the methane being released, like I said, I made an initial assumption that it was pure methane that's being released as a flux. And those numbers are derived from experimental data in the coal mine. People found concentration rates down here. They're saying that the methane was 100 CFM, which is really just a fraction of the total flow to kind of take out that what the concentration of methane was. So we kind of redistributed that through here, and it may not have actually been 100% methane being released, since the methane content of coal, I think, is believed 20 to 60% or something like that.
I see. Yeah, yes, thank you. Just was comment from the audience. And yeah, I did not face it as the first point. So you use some model, right? I think you talk about K-epsilon model. So
Yep.
as long as you incorporate model, it means that, yeah, you use K-epsilon model. So it means that it's not direct numerical simulations because some models incorporated, so you don't resolve everything. So,
Right.
but it's not filtering here, so it runs. It's Reynolds average Navier-Stokes equation, but I believe unsteady runs as long as you talk about transient phenomena, right?
Mm-hmm.
So it should be unsteady runs with K epsilon model. And so what about transient? You talk about transient phenomena, right? So what, do you have time dependent somewhere? Did you show any plot? I saw you plot, you have plots, but it was not transient, I believe. Could you?
So what I did, I got different results when I tried running the steady state versus the transient model. I went into the transient to see if I could stop it at different time to see time depend, because really I eventually want to get some time dependency here to figure out how long does it take for these concentrations to reach a certain point. In the coal mine, we want to say, this is what the concentration is now. How long is it going to take until it reaches this and becomes a dangerous level, so that we can avoid that? Because that's ultimately what I have to combat with the system response of our system. If our system takes 20 seconds, 30 seconds to response, is that too late? Is that fine? So I was trying to use the transient to stop it at certain points to see what these profiles were, but this was ran until everything seemed to converge and reach a steady state. This was the maximum concentration that I was able to achieve. Because air is constantly flowing, both of these velocities are constant right now. I have this fixed as a constant entrance of air and a constant flux of methane.
Okay. Okay, yeah.
Yeah.
Yeah, I see. So any more questions from the audience? Regarding anything? So yeah, that's nice. Yeah, and that's really nice work. And when you talk, but you don't have coal particles here, right?
No, I do not. Like I said, I have not incorporated any of that stuff yet. I'm currently working more on this stuff now. So this was something we were just trying to get some baseline results, some just initial kind of first pass stuff in the last couple of weeks.
Mm-hmm. I see. And so if you're going to incorporate coal particles, so what will be distribution of coal? Do you have any idea?
We had used some values. So when we developed the whole system, apart from the CFD stuff, we had done a little coal particle simulation on a filter, because we have filters that have to filter out the air sample for our system.
Mm-hmm.
So we had a number somewhere. I don't have any of those up with me right now, but we had a work somewhere that described kind of the particle count expected throughout the production. But that would obviously change too. The issue is, as the shear moves back and forth, so things get really dusty and messy around where the cutting is being performed in that instance. So yeah, it would be a function of production. I would incorporate that in, I guess, as something that maybe is, the source would be the shear. So particles would be released as you cut the coal.
Okay. Well, I also don't know about distributions. In fact, so far, typically when I deal with coal distributions in a mine, I started with like classical distribution, like parabolic, hyperbolic, linear, polynomial, cosine, sine, to see that. But it's like when you start some fundamental study, it's easy to implement whatever you want. But
Yeah.
I don't know in reality how it is, and that's a serious point, serious question.
Yeah, and things are changing because they've combated this a lot with sprayers. There's a lot of water being sprayed down on the active cutting, so they try to minimize all that stuff. And it's really tough from our end too, especially for the CFD stuff, to get a lot of initial conditions and boundary conditions, because it's simply the values just aren't out there.
All right.
So.
All right. Okay, thank you. So any more questions from the audience, please? Okay, let's thank our speaker again. Let's thank you. Thank you. And let me just stop.